If you've ever tried running a large language model over a long document or an extended conversation, you've probably hit a wall. The model starts to stall, or worse, it completely forgets what was said at the beginning. The bottleneck is the model's weights. It's the KV cache. During autoregressive generation, every new token requires the model to attend to all previous tokens. To avoid recomputing, the attention mechanism stores the key and value projections for every past token. But attention scales linearly with context length, and that cache grows with each new token. At 50,000 tokens, you're looking at gigabytes of memory. At 500,000, you're talking terabytes. That's enough to max out even the most expensive data center GPUs, and it creates a severe memory bandwidth bottleneck that grinds inference to a halt. The standard fix has been quantization. You take those high-precision floating-point keys and values and compress them into lower-bit formats, like 4-bit or 8-bit integers. It's effective, but most implementations treat the entire cache as a uniform block. They apply the same bit width across every token and every position. The problem is that not all information in the cache is created equal. Some tokens carry heavy semantic weight, some positions are critical for long-range dependencies, and some are just noise. Uniform quantization wastes bits on low-signal areas and destroys precision where it actually matters, which is why you see accuracy collapse on long-context retrieval tasks. This is where structure-aware quantization, specifically a method called Block-GTQ, changes the paradigm. To understand why it works, we need to look at how modern models encode position. They use rotary position embeddings, or RoP. RoP rotates the query and key vectors in a two-dimensional plane based on their position in the sequence. When you decompose the attention computation under RoP, the interaction between queries and keys naturally separates into independent two-dimensional frequency planes. Each plane corresponds to a specific rotational frequency, and each carries a different mix of positional and semantic information. Here's the critical insight. These frequency planes don't contribute equally to the attention output. Some handle high-frequency positional shifts, which are highly sensitive to compression artifacts. Others carry low-frequency semantic trends that are robust to quantization. Block-GTQ measures this by calculating an energy score for each RoP block. It evaluates how much query key information flows through that specific frequency dimension during the attention mechanism. High-energy blocks are highly sensitive to precision loss. Low-energy blocks can tolerate aggressive compression without degrading the output. Instead of applying a flat bit width, Block-GTQ uses a greedy allocation algorithm. You give it a fixed memory budget, and it distributes bits across the frequency blocks based on their energy scores. High-signal blocks get higher precision, often staying at 8-bit or even 16-bit, while low-signal blocks get compressed down to 2-bit or 3-bit. The total cache size stays identical, but the information density is optimized. It's not just quantization. It's quantization guided by the underlying mathematical structure of the attention mechanism. The results are striking. When tested across modern transformer architectures, this targeted allocation slashes attention approximation errors by over 30% compared to uniform quantization. But the real validation comes from long-context benchmarks. In the needle-in-a-haystack test, where a single fact is buried in up to 500,000 tokens of filler text, uniform quantization completely breaks down. The model loses the ability to track the needle across long distances. Block-GTQ, however, maintains near-perfect retrieval accuracy. It keeps the structural integrity of the cache intact exactly where the attention mechanism needs it. They also ran the models through multi-document question answering, long-form summarization, code completion, and complex classification tasks. Perplexity, which measures how well the model predicts the next token, stayed within a few percentage points of the unquantized baseline across all context lengths. Uniform quantization saw perplexity skyrocket, confirming that oversquishing the cache destroys long-range reasoning. On the hardware side, the memory footprint dropped by more than 3 times. At short contexts, decoding uncompressed data is technically faster, but as the sequence grows, the memory bandwidth bottleneck kicks in. The compressed cache actually pulls ahead in sustained throughput, and crucially, it's the only method that avoids out-of-memory crashes at extreme lengths. What makes this approach so powerful is that it doesn't require architectural changes or heavy post-training fine-tuning. It's a lightweight, inference-time optimization that works directly with how modern attention is built. As we push language models to process entire books, hours of transcripts, and complex multi-step reasoning pipelines, raw parameter count is no longer the only bottleneck. Memory efficiency and attention precision will be just as important. Block-GTQ shows that by respecting the underlying mathematics of how these models process information, we can build systems that are cheaper to run, faster at scale, and genuinely more capable with long context. And that's exactly the kind of targeted optimization that moves long context AI from experimental benchmarks into reliable, production-grade applications.